Okay, with a few scripts to help us out, some things we can poke into our blockchain and find out information or change things. Let's take a look at a payment contract. This is kind of a general payment contract that you'd use in conjunction with some piece of outside software so that you could receive payments in Ethereum, and then this generates an event to tell the outside software, yeah, I got paid for something, do something. So we've got up at the top of Pragma an import that's fairly standard. It's just ownable. And we have a contract. The first thing that we do in this contract, line 7, is we see that we have the address of the owner. So obviously it's doing something with that address, probably created in the constructor. We've got two events of interest in here. The first is receive funds. And we find out who sent the funds, the amount that they sent, okay, the application, and whatever this loc is. We'll find those out in a minute. And event withdrawn is how much we've transferred of money that the contract has received out of the contract, so we've transferred it to some other account. And we keep track of some other things in the account that we can probably get access to later. There's one map that is the map based on an address, which is some sender of funds, to the amount that they've sent in and the total amount that we've received from that person. So let's take a look at the constructor. It does about what you'd expect since there was an owner address. It saves that address as the message sender, which in the context of the constructor is the person who's creating the contract or the owner of the contract. The primary function in this is receive funds. And this is the one that when somebody is paying for something, they would call. And it has, for a particular product, it's payable, which means it takes funds, and it returns success, I would guess, is what the return is. So we count the number of payments. We do something to get the length of the list of total payments. We save who the sender is and the amount that they sent. And we keep track of which product they've sent money for. Okay? We get a total by account. So for every account that there is, we are also keeping a total for that. We add up that total, and then we generate an event that we can see later by some other outside piece of software to tell us, yeah, they sent money for some particular thing. The rest of the stuff in this contract is how we get info back out of the contract afterwards, and some stuff to do a withdrawal at the end to indicate that, yeah, we can transfer the money out of this contract. So we can get the number of payments, and we can get the payment info on a particular kind of thing. So we can find out some information. And you may want to add some additional, if you're actually going to use this, you may want to think through and add some additional functionality in getting out the payments. But primarily what this thing does is this one function to collect payments and generate an event. You'll notice that in here for these arrays, that it just simply adds to the end of the arrays. It pushes new data onto those arrays to save it in the arrays. So this particular payment contract, it's not super fancy, but if you were selling, some digital product that you wanted to say, I'll take payments in Ethereum. Once I've got the payment and I know that I've received it, then I'll send you an email with the final result. You're selling a digital course on how to do Solidity in Ethereum. Okay? That would be the kind of a contract you would use to receive payments for it. And you don't have any of your stuff stored on the blockchain, but what you have is, here's the method to receive payments. Okay. I like this quote, okay? I think the first time I saw it was in relationship to something that Dennis Ritchie wrote called Unix. But software that is not tested is broken. And I think that that's true. Certainly I have written lots of broken software because I failed to test something or I didn't test it enough. And how do we know in a contract that the results are correct? There's lots of different kinds of incorrect. If we build contracts like solidity where it's Turing complete, but we have a bound on the length of execution to prevent things from running too long. That's what the gas is there for. It's also how you pay for running contracts. One of those criteria is that everything finishes in time. If it doesn't finish fast enough, it's broken. But that's not all that testing can tell you on something like this. It can tell you if you got the right kind of result. As in, if I sent in a payment, did I receive the payment? Did I generate the event? Did I do enough to actually see that, yeah, I got the results I'm expecting to get? And as I'm working on the contract and maybe I go back to add some new feature to it, a new accessor to get the data back out, something I forgot that isn't in there. These tests, if they're done right, if they're done in the way that can be repeated, then I can turn around and I can continue to test the existing stuff over and over and over and verify that it still does what it's supposed to, that I haven't changed an interface, that it still produces the correct kind of results, the correct kind of events. I want to talk a little bit about the value of code review. Code review is not a popular subject, but it should be. Most of the time, you find the most defects through code review. I mean, we can look at unit testing. We talk about unit testing in a number of classes. Microsoft has done a lot of research on what works effectively to fix and prevent defects. Unit testing will find 23% of the defects in a piece of software. Okay. Integration testing is when you take all the different pieces of the software, put it all together, and usually you have a quality assurance department do tests on it. Sometimes you have a group of developers, but you put it all together and you test it all together as one piece. That will find about 28%, and it has a significant overlap with what you found in unit testing. If you release your software to a beta group to test it, you'll find another set of around 30%. Now, there's one thing that will find more tests than anything else. The problem with a lot of things like unit tests is unit tests test for what is in the code. But lots of defects are not what's in the code, they're what was left out of the code. They're an if case that doesn't have an else. There's something that isn't there that needs to be there. And there's one system that finds this better than anything else, and that's code review. Code review, actually done right, will find 67% of all the defects in software. It finds more than any other thing, more than beta testing, more than integration testing, because lots of times good code reviewers will look at it and say, what about this other logic case that you forgot to take into consideration? Or in the documentation for this, the design, it says we're supposed to do this, but you did this, and these don't seem to match up. Explain it. And sometimes it's implemented right. Sometimes the explanation is it's good. And this is a wonderful thing. But code review takes a lot of time. A code review well done, you take somebody's piece of code and first you run their unit tests and then you read the documentation. Then you go through the code line by line and read it. Then maybe you write some more tests that get included in the unit tests. And then you say finally, this address up here is not the same as this address down here. Why? Or what happened to this? Or what's the logic behind this? Or why do you do these two tests and the tests are basically the same? Is it useful to test it twice? If so, what are you getting from this extra test? Sometimes the answer is, we don't need that. Why is that in there? Okay? So unit code review is vastly useful. And in testing in the real world, okay, not only code review, but very often security auditing, which is a particular specific kind of code review, is the way that a lot of these things are fixed and made to work. Now, you can't make a really, really nice piece of code like the Daedalus wallet with just code review, but you can find an awful lot of problems. It takes design and forethought and sometimes reworking. One of the nice things about having automated tests is when you do go to rework and rewrite something, hopefully your automated tests will tell you if the new version you're building still does what the old version used to. And lots of times that's what you end up doing is you write it, you build tests. Then you go back and you say, no, this isn't working right for whatever reason. You rewrite it. And now you run your old test to verify that the new version still does what the old version did and fixes the problem you're trying to fix. So, different ways of testing. There's think testing. I'm not too fond of think testing. I prefer to actually get out in front of the computer and actually sit down and use the testing software or write testing software. Some languages are more prone to think testing than others. It depends on how effectively you can get output from the language. And getting output sometimes is very difficult. A good example of think testing is Excel spreadsheets. People put in stuff and then they look at it and they think to themselves, is that the right result? There are more defects in the functional programming of Excel spreadsheets than anything else. And defects that are hugely important. For instance, there is this book by Plinke, I think it is. It's an economist in which he reviews the difference value of capital and labor in the past 50 years. And if you actually got his spreadsheet and looked at his spreadsheet, at some point in the spreadsheet, he went in and added stuff up, but he left 5 countries out of his addition. And if you include the 5 countries, you come to a different conclusion. A national economic policy is being built on this information that is in, and the guy got a Nobel Prize. And he left 5 countries out. Obviously, there was no code review. Obviously, there was no unit testing of this. So, think testing has a lot of disadvantages. An awful lot of university software, this is all you do for testing. You don't actually set up and build unit tests. Unit tests, I talked a little bit about it. It'll find 28% of defects. I would think unit testing is like a first step in testing. You build some software, you go back to what your specification is, you say, did I produce a test for everything that it can do? Did I do reachability, where I've made certain that the tests that I've got in my unit test exercise every piece of code on the inside of it? Have I left anything out? It's fading in popularity now, but a mantra of test-driven development, or TDD. TDD is absolutely a wonderful thing in certain contexts. It works. I was doing a project down in Denver a couple years back where we had this Java WebSphere application that we wanted to replace. This is for a customer, a contract. We wanted to replace with something faster. I suggested to them doing it in Go. We finally did do that. And we managed to swap this over and get it to work on the first try in the middle of the night. We took their data center, which was leased. It wasn't in their data center. But it went from 28 computers, big expensive computers, costing them $3,000 to $5,000 a month per computer at Amazon Web Services, down to 2 that were not very heavily loaded. And the way we did that was test-driven development. We took their existing software, and the first thing we did is we built tests for every API interface in their existing software. Then we tested the test carefully. Then we took a week's worth of all the requests that had come into their application, and we saved every single bit of every request and every response. And we built that into a test case that we used against the old software, a copy of it, to rerun it. It's an expensive test when you've got to set up multiple computers to do it. And against the new software that we built. And we verified that it matched with the behavior of all the tests that we'd already built. And we built new tests to test the things that we found out of that sample set of data. And you notice we're building tests primarily here. Then when we got all that stuff done, we went back to the new version of the software and we said, okay, from the tests, I'll build the specification. From the specification, I'll build the software and make certain that the software works against this test. Meanwhile, a couple months is going by and we are collecting every request that they've had across months. And we turn around and use that as a new test in our test-driven development to run it against the new code in Go. And guess what? When we got done, we had something much faster, much better. We eliminated tremendous amounts of technical debt. And so test-driven development is really, really good. if you're doing a second version of something and you know how it's supposed to work. If when you do the second version, you don't say to them every time they want to add a new feature, no, let's get the existing features to work with the new system. Not let's change it somehow and make it so that we break our tests. So it can be a useful thing if it's done the right way. If it's done the wrong way, as in you're building a new version of something that you've never built before, you don't know enough when you start building it to build the tests. And you may think you do, but you don't until you've actually built it. Software is all about the details, and I can prove this. If you have a program and you change just one bit in it someplace, it behaves differently. Maybe only a little bit, maybe it core dumps and fails completely. Maybe it changes the results of something in some subtle way. But all software works this way. It's digital. It either is or it isn't. There's no in between. It's not like the linear world where, the cup can be 3/4 full or 3/8 full or 9/10 full. There's no linearity in most digital systems. It either is or it isn't. So as soon as you take something and you say, I'm going to build something exactly the same as it was, but I'm going to get rid of the technical debt, then it'll work. But when you're building something completely new, you don't know where the problems really are until you've built it once. Maybe twice, maybe 3 times. Maybe you build it 4 times in a row, and by then you go, okay, these are the problems I've got to overcome, and these are the things that I really need in my test-driven development. And at that point, yeah, test-driven development is good. Before that point, it's a bad plan. And on things that are actually innovative, it's a really bad plan. I mean, if what you're building is a bunch of forms to collect some data to update a database, and basically it's going to produce inserts and updates on a table, yeah, you've built it before. It's not some new innovative thing. So integration testing. Integration testing is when you put all the pieces together. And lots of software tends to fall down at the level of integration testing. First of all, people get behind and they squeeze their test schedule down and they don't do all the testing they should and they leave stuff out. That's horrible. I mean, if it's behind, it's behind. You got to deal with that, or you got to cancel the project. There's no squeeze it down to be in a smaller period of time and test faster. Integration testing should probably also include performance tests and scale tests. And if this has to work at scale, then you're going to have to do something to simulate that scale accurately. And you need to be building simulators or emulators that will run that scale. But when you get to the integration testing for something like a web server, lots of unit testing tools that have been great when you were testing a piece of code just don't work because you've stepped up a level and now all the code is put together and it's all in one big monolithic piece. I do a lot of integration testing for APIs using curl, the same thing we saw at the beginning of the lecture, to actually run in series requests against an entire API. And recently I've built testing tools specifically for testing entire APIs so that you can do integration testing and get results based on the top level of a system. And the last thing I'd like to talk about testing is formally proving tests. This is a burgeoning field, and this has been something that the University of Wyoming has been teaching in some degree for decades. It's certainly something that brought me a number of really high-paying jobs over the years as contract work. But formally proving systems is becoming increasingly important. And we have more and more things that, if they're not thoroughly tested, result in cataclysmic results. Boeing 737 MAX, for example. You really don't want your software to fail while flying an airplane with it. And we're coming up on self-driving cars. And you really don't want those self-driving cars to all suddenly fail together. And everybody takes a hard 90-degree turn and flips their car over. These are the kinds of things that have horrendous results. And in a blockchain, your successes can be finite, but your errors are forever. This is just like sending software to space. You have to test it, and you have to test it thoroughly. And the best testing you can do is formally proving the results. Lots of hardware, CPUs, are formally proven because the cost of making mistakes is so high. Intel had an error in doing division of floating point numbers. Between the recall of the chips and the replacement of motherboards and their loss of sales, that one small flaw that only happened in about 1 in a million computations cost them close to $2 billion. At those kind of price rates, do you think they formally verify what they're doing these days? You bet. They spend a lot of time making certain that every instruction does what it's supposed to do, not some of the time, but all the time. So, formally proving things. Blockchain is a perfect example. And one of those things is Solidity doesn't lend itself, since it's an imperative language, to formally proving. Whereas a pure functional language like Haskell applied to blockchain, especially since the data that you're taking in the previous block and the inputs are a pure functional set of data to produce a new block that's a pure functional output, would be a tremendous thing. And using a system that makes it easier to, even easier than Haskell, to prove completeness and that things run in finite time and that they produce the correct results is a tremendous boon to getting accurate results, not just some of the time, but all the time in these financial computations. And the stakes are very high. There's a company that had raised hundreds of millions of dollars of capital, but they had a mistake in one of their contracts. And it so turns out that their mistake could be triggered by, guess who? One of their competitors? And this competitor, who had always raised hundreds of millions of dollars, realized this, and they say they didn't do it intentionally. But they did it. And when they did it, it was not undoable. And that company lost $157 million of other people's money because they goofed up a single contract. And there was no going back. They couldn't get it back. They couldn't do anything. It was just gone. So, formally proving. What's a good example of formal proofs in functional systems? Microsoft has been working on a replacement for their TLS stack. It's currently written in C++, but they've been working on one in F# and doing formal proofs to prove that every step of the entire process is provably correct. And this is a huge undertaking, and the reason they're doing it is because billions of dollars of commerce are protected by this. This is what underlies HTTPS on the web for all of the browsers that are browser and applications that Microsoft does. So billions of dollars are at stake, and they're working through the process of formally proving that it has no mistakes. And that is not a trivial thing to formally prove, but there's so much value involved that it's critical. So especially with contracts, okay, making certain that the contract is simple and works well and has thorough testing is critically important. Now with Truffle, there are two different kinds of tests.